Okay, so since we are not going to have class on Thursday, I did want to go ahead and do the first pre-lab sort of questions on the lab sheet, the first pre-lab calculation. All four calculations are exactly the same, and they're asking you to calculate the energy of each of hydrogen's visible spectrum colors of light. So the first one is the 410 nanometer wavelength of light. So the question is asking you to find the energy, and they've given you wavelength. So when you look on your calculation sheet, you have one formula that includes both of those things. And that formula is E equals H times C over lambda. So remember that H is Planck's constant, and it's 6.626 times 10 to the negative 34th joule seconds, so that's joule times seconds. C is the speed of light, 2.998 times 10 to the 8th meters per second. Our energy answer will be in joules, and I was given the wavelength of 410 nanometers. But the problem here is it's in nanometers, and to cancel out this, I need it to just be in meters. Well, that's easy enough because I know that nano is times 10 to the negative 9. So that's 410 times 10 to the negative 9 meters, because that's what nano means, is times 10 to the negative 9. So I now have all three numbers, and I can simply plug them in to my formula. So energy would be equal to Planck's constant, 6.626 times 10 to the negative 34 joule seconds, times that speed of light, 2.998 times 10 to the 8th meters per second, all divided by that wavelength of 410 times 10 to the negative 9th meters. Now, if I remember correctly, I think on your on the lab itself, I put a period right here, a decimal. So this should be 3 sig figs when I do this. So in your calculator, everything has got scientific notation. So 6.626 EE negative 34 times 2.998 EE8 divided by 410 EE negative 9. So 6.626, 10 to the negative 34 times 2.998 EE8 divided by 410 EE negative 9. And that is going to give me an energy value to 3 sig figs of 4.85 times 10 to the negative 19th joules. Remember in class, I said all of your answers are going to be in this times 10 to the negative 19 range. That's how you know that you've done it correctly. Okay, so the other three pre-lab calculations are just like that. So the next thing to do in this lab is actually to burn the stuff. So I'm gonna have to switch cameras here, and it's gonna be dark because how else are you gonna be able to see the colors? So we do that. We are switching, stop that share, switching cameras. All right. Okay, so what you can't see here is that I've got the blowtorch. So let me turn it on. Okay. So the blowtorch is normally a nice blue flame. And I'm gonna go in order here. So all I'm doing is dipping a stick in some of the salt. So this is the lithium ion. All right. So we typically describe that lithium color as almost a magenta. It's so pink. So that's the lithium. On your periodic table right next to it, right below it is sodium. And again, if you've ever made a mess in the kitchen and boiled over water, you're going to be used to this color. It is a very, very vibrant, light orange yellow. Very, very distinct color. That was sodium. The next on your list is actually probably the hardest one to see, and that's potassium, directly below sodium. So far we've had like a magenta, we've had a yellow orange. Potassium is kind of in that same range. It's actually a combination of a peach and a violet, which is hard to see because it's in the blue. But you do get a peachy and a violet color with the potassium. Okay. Next, right next to potassium is calcium. All right, let's see if the calcium is going to behave for us. All right, the thing to note about the calcium is it is slightly orangier than the sodium. So some people say that the sodium is kind of like the Cheeto Puffs sort of color, and the calcium is more like a regular Cheeto color, just slightly darker, you know? All right, next is going to be strontium, which is below calcium. So it's going to be a similar color range. And in fact, calcium and strontium are almost exactly the same color. You can sometimes get strontium to be a little bit more red, so it might be a little more flaming hot Cheeto, a little less regular Cheeto. Below strontium, you get barium. Now, barium's got the most electrons of any of the things we're testing. But we are going to stick with a similar sort of color range here. Except it's so pale yellow, it almost looks white in the camera. So barium gives us that super pale yellow, almost white. And I'm sure you're sick of me sticking orange things in the flame, so we'll change it up. This next one is copper. And if you imagine what color copper compounds are, well, it makes it a little easier to see this. Okay. All right, well, if we think of copper getting a nice patina green color on it, then it makes sense that copper gives us a green flame. That is one of the prettier flame colors. And then our last one is tiny little boron. Boron is over there next to carbon. And if you notice, what we're burning right now in the tank is carbon. So the blue color is coming from carbon. And boron's right next to it. So even though it doesn't have very many electrons, it also gives us a green color. But it's a lighter color green than copper's, and it's got a hint of orange in it. All right. Okay. So again, that's copper. That's the boron, right? It's a grass green, more of an emerald green in comparison. So that's the flame test. I'm sorry you're not here to burn it on your own, but I will say, if you ever want to make colored pine cones, the boron comes from boric acid, which you can find in the hardware store. And you can make a paste of boric acid, which is going to be around where you do ant. You'll find it in the same aisle where you find ant bait. And if you make a paste out of boric acid, you can spread it all over a pine cone and then let it dry and toss your pine cone in the fire later, and your fire will burn green. So there you go. That's what you need to do next.